Everything, if you want to tune your code, you can do so. We'll skip through this, we don't need to care too much about that. You can also tell it things, so you can say, well, there is a loop here, or a parallel thing here, but actually I want this part which is doing sequentially, because it's a bit of the code, I need the data on this GPU, but it doesn't want to be running parallel. You can also say this loop is independent, because part of the compiler is finding it quite hard to say can it parallelize this loop or not, so you can tell it. It may look like there's points of arithmetic in here, but this loop is actually independent. You can run it independently on the GPU. You also have conditional execution clauses, so if something's true, then run it on the GPU, otherwise just run it on the CPU, so don't launch the kernel. So for instance, you could say, you could have a routine which is used to arrays of different sizes, and if the array size is small, you just want to run it on the CPU, and if the array size is big, you want to run it on the GPU. That'll do everything. And we have reductions, like you do in OpenMP. So you can say, I'm going to take this and I'm going to sum up this array, do that for me sensibly. And it will. But coming back to the point you made, what happens to the data? If you consider this bit of code here, which we saw before, this parallel loop and this parallel loop here, what's going to happen here by default is when we hit this parallel at the top here, it's going to copy input and output onto the device. And then at the end here, it's going to copy them both back out again. And then we'll run down here, and then it'll copy input, it'll copy output, so back into the device, do some work on it, and then copy it back out again. So we've probably got 3 more copies there than we need. We don't need input to be copied back off the device here. We don't need output to be copied back off the device here. And we don't need output to be copied into the device here. Okay. We just want output to stay there until we've done this work. And then maybe we need it at the end here, so we'll copy it back. So how do you do that in OpenACC? Well, it has a data clause as well. So it has a way of saying, specifying what happens to data inside a particular region. And these regions here don't have to be the same as your parallel regions. So you can have a data clause for your whole program saying, copy this data at the beginning and copy it out at the end. And then you can have lots of parallel regions inside the program which just use the data that's already there. And this is the way they try and get around this. Okay, so for your data clause, you can have copy, copy in, copy out, create, private, first private, or present. You can have all these different modifiers, so you can say, copy this, copy means copy in and out. Copy in, bring in and out again. So you can say, copy in, you would say copy in input, and copy out, and copy output on your data region. And you can also say present, say, I know I'm running parallel here, but I know the data's already on the GPU, just use the data that's already there. So in that example we had before, no, it's not that example we had before. A different example, we've got a main program which is called a subroutine, which is doing some kind of operation in the array. But we actually know that although the data, although the dummy array over here in Fortran is called B, we actually know it's this A data here, which we've already got on the GPU, we've already processed it here. So we don't want to have to copy it onto the GPU and have to get here again. So we have a data region, we say copy A. So that means at the beginning of the data region, it'll copy A into the GPU, and then at the end of the data region, it'll copy it back out. And then here on the parallel loops, okay, it doesn't need to copy it, it already knows it's inside the data region, already knows it is there. And then on this loop, which is called in here, we can say B is actually present. You might want to copy it, but we know it's already there. So don't copy it, it won't, it'll just work, and at the end we just copy it back. And then there are other directives. So update directive lets you say, I want to take this little chunk of data and copy it back to the CPU, or this chunk and copy it over here. Stuff like that. As I said, there were 2 different models inside OpenACC. One is with parallel, which is looked at. There's also one called kernels, which does a very similar kind of thing, slightly different. But instead of doing a parallel loop, you can do a kernel loop instead. Do slightly different things, but you don't have to worry about it. And then there are a set of, So is there any questions about the programming of GPU? I appreciate a lot of it doesn't really make, well, at least to me, a lot of these things never really make sense until you actually try and do things in practice. But what we can see there actually is all the models are quite similar. CUDA and OpenCL are more similar than we'd like to admit. They do very similar kind of things. They have an abstraction of the GPU, and they try and map the data to that abstraction, and they give you functions to say, turn this into a kernel and run it, copy this data backwards and forwards. Okay? And in that scenario, you have to take your code and you have to physically change it to run on the computer, on the GPU. And it's up to you to decide what runs where and how the data gets moved. OpenACC and OpenMP4, when it comes along, is a way of trying to do the same thing but not have two different codes, one for GPU and one for CPU, and it will try and manage the data copies for you and the scheduling of the loops and stuff like that for you. But it still has this concept of different blocks on the GPU and different thread groups inside those blocks. It's just you're not usually specifying exactly how you map to. In reality, both are hard to do for big codes. Both require work. I mean, the CUDA OpenCL option is fine, but a lot of people don't want to have two versions of their code. Right? You know, it sounds trivial, but a lot of big scientific simulation packages, if you have to maintain two versions of your code, that's a real problem. If you find a bug, you've got to fix it in two places. You have two source codes which start to diverge, it becomes really, really problematic. That would mean that the OpenACC, the directed approach, should be more preferable, but there are problems there as well because the compilers are not as mature as you would like, and they can't do all the things you like. So there's things called deep copy functionality, which we can't do, which is if you have a derived type in C or Fortran, i.e. a type which references other types, at the moment you can't use those in data routines. It doesn't understand how to copy those backwards and forwards. They're working on new models of doing that. It's also much more restrictive on how you do your program. So I'll show you examples later. There are a lot of nice language features in like C and Fortran you'd like to use, which OpenACC compilers will just say, I don't understand what's going on there. I can't trust what's going on there, so I can't turn that into GPU code. So neither are ideal solutions. I'm part of the OpenACC standards body, so I'm bound to say that OpenACC is the better way to do it. But I mean, neither are really ideal solutions for anyone they would think at the moment. Ideally, what you would have is the compiler would just do it all for you. It would just turn your code into GPU code and it goes. But it's very hard to do. That was programming GPUs. What about Xeon Phi? How do you program Xeon Phi? Yeah.
A question about the data locality present directive.
Yeah.
Is that actually going to automatically keep a copy of your data from the main memory to the GPU, something like that?
It just tells it you've already copied the data there, and you're guaranteed it's already in the location and already up to date.
So you have to do it on your own.
Yeah,
so
so you're saying, so if you've messed it up on the CPU, it won't. That change won't be propagated unless you tell it, unless you say update it on the GPU. So you're in charge there, and actually, yeah. So it's all down to you. If you say it's present, then it's just going to assume that the variable that it has, the array it has, is the correct copy.
Okay, so that sounds similar to what the cells were doing with the local store. That it's basically there, and you don't have to copy in, copy out, which takes the most amount of time, basically.
Yeah. You have an update directive in OpenACC which lets you say, copy from the host and update it, or you can say copy this small part and update it because that bit's changed. That's the way it works. Okay, so for the Xeon Phi, as I said before, the nice thing about Xeon Phi, theoretically, is that the CPU cores are more complicated, so they can run proper programs, and they actually run an operating system. There are multiple ways of running on the Xeon Phi. Okay? So you can recompile your program with Intel compilers and just run it on the Xeon Phi most of the time. Okay? That's called native mode. And that's just the way you rebuild your program and you run it. Of course, if your program uses libraries, they'd all have to be rebuilt for Xeon Phi as well. Okay. You can do that. There's something called offload, and this is much more like GPU programming. This is you say, here's a kernel, I want you to run that on the Phi whilst my main program is normally run on CPU. So you compile your main program for CPU, it generates some offload kernels and it runs them separately on the Phi, and you have to control the data backwards and forwards movement. And then there's symmetric, which is you can run across both CPU and the Xeon Phi at the same time. Now you can only really do this using NPI, but you can run a program which runs on the Xeon Phi and across multiple Xeon Phis and with multiple CPUs at the same time. So you can use OpenMP and NPI or hybrid codes on the Xeon Phi. You need the Intel compiler and the NPI libraries to do this. You can also use Intel's MKL maths library, which has been optimized for this. For the Xeon Phi, so you can offload maths stuff using MKL onto the Xeon Phi. And Intel's Click and TBB, so Click is a C++ programming environment. Thread building blocks is a C++ programming environment, I believe. So it's not Click, is it? It's simple. Can be used as well. But as I've said, nearly all our code is C and Fortran, so we can really play with thread building blocks or so.
So if you have your code already using NPI,
Yeah.
then how
You
much,
can just read, well, how much performance you get.
well, I was going to say, how much hassle is it to
Well, so generally you can just rebuild it and it works, just recompile it and it will run, generally. But that's not to say you'll get good performance. Yeah. If you want to do the offload model where you're doing something quite like the CPUs, GPUs, how do you do that? Well, we have these offload, so you can see we have this, again, pre-processing directives, pragmas, offload, attributes, and in Fortran, Intel's specific pre-processing directives, and also offload after that attributes. So you do something like, you can also do the same with data transfer. You say, in the pre-processing directive, you say, transfer this data from here to here, transfer this code from here to here. So it would look something like this. If we did another vector operation here, we'd be doing this bit of code here, and we have a hash pattern, an offload target, like 0, so you might have multiple accelerator Xeon Phi cards, as you say, really on the first of them, copy this data onto the card, and run this calculation on the Xeon Phi. And this will take your code and run the Xeon Phi for you to compile it. So it's a sort of a little bit more like the OpenACC way of doing things, but a little bit more involved. There's also, I'm not going to go into details, I'm going to really use it. We don't really do offloading very much, we do mainly native stuff. Because again, we're not looking to, the kind of programs we're doing are big MPI programs which don't really match well with this offloading model. But there's also an implicit way of doing this offloading, which is something called virtual shared memory. So the user declares objects to be shared, and then the data is allocated both on the host and the Xeon Phi. And it will implicitly copy the data backwards and forwards when you change it in either place. At various points you say synchronize here, and it will do that copy for you, and it lets you offload the code that way. So you can either manage the memory directly yourself in this offload model, or you can use a virtual shared memory. But primarily, so a lot of people do work with the offload model and just kicking various kernels off onto the Xeon Phi and load the data back again. But primarily, we work on the native mode where you recompile your program and run it with the Xeon Phi. And of course, the Xeon Phi has this architecture. You've got 60 cores, each can run 4 threads. To actually get any performance at all, you need to be running a minimum